First, improvement based on interim presentation. Instead of valve and heater for product and byproduct standardized in room temperature and 1 atm. This is a before we put valve and heater, and this is after we put valve and heater to standardize the byproduct in 1 atm. Reason of operating flash column C1 at very low temperature, -75°C, is because flash column separated between ethylene, carbon monoxide, hydrogen, ethane, and propanol, and the boiling point for chemical are, and the operating temperature of flash column should be between the boiling point of C2H6 and C3H6O because we want to spread between them. And recommendation temperature from articles state the ranging temperature for flash column from -80 up to -50. Stream S30 is a mixture of components which require low purity. Why do not subject the stream to a separator for further purification process in order to increase the product value? First, for stream 30, it consists of high amount of DPE, propanol, and hydrogen. DPE can act as solvent for animal, vegetable, mineral oils, wax, and resins, extraction of acetic acid from aqueous solutions, solvent for dyes in presence of small amount of alcohol, supporting composition, paint, and varnish, rubber cements. Therefore, DPE will be further spread up to 99% of purity and sell to other industry with price of $3.2 per kilogram. Hydrogen will be further spread also and recycled back into the reactor R02 in order to produce a high amount of propanol. Meanwhile, propanol is used in the manufacture of plastics, in the synthesis of rubber chemicals, and as a disinfectant and preservative. Propanol is a colorless, flammable liquid with a suffocating fruity odor. Hence, this component will be selling to other industry at the price of $16 per kilogram. Next, heat integration. First is the stream data extraction. This is our stream data extraction, and this is the minimum that we use on the hot stream, which is 10 degrees Celsius will be minus from their temperature and will be the temperature adjust. Problem table algorithm. The shifted temperature and enthalpy data from stream data extraction will be inserted into this problem table algorithm. Heat cascade diagram. A heat cascade diagram will be drawn accordingly to locate the hot and cool pitch temperature as well as their target or minimum heating and cooling requirement for the entire plant. And for the hot pinch temperature is a 699.53 degrees Celsius, and for cool pinch temperature is a 689.53 degrees Celsius, and for minimum hot requirement is a 0, and for cooling requirement is a 8.19 power of 8 kilojoule per hour. Grid diagram. This grid diagram we have trial and error for many times until we manage to same exactly with the cooling requirement, which is 8.19 power of 8. From step before, we extract the data which are hot pitch temperature is at 699.53 degrees Celsius, cool pitch temperature is at 689.53 degrees Celsius, and minimum heating requirement which is 0, and minimum cooling requirement which is 8.19 power of 8, and heating requirement before integration and cooling requirement before integration. Percentage utility savings. It turns out that despite the number of streams for heat exchanger has been reduced, the percentage saving for both external heating and cooling was still astoundingly high, with whopping amounts of 100% and 28.66% respectively. So we can save as much as 44.53% of utility energy usage. Although a lot of heat exchanger may be required to achieve this target, the implementation of the tedious heat exchanger network is ultimately worth the cost, as a large amount of utility costs can be minimized in the long term. PFT after heat integration. Before integration, there are 6 cooler and 6 heater that being used. After integration, we managed to reduce heater from 6 to 0 and cooler from 6 to 3 cooler, and there are 9 heat integration process happen.
Next, we're moving on to optimization. Generally, the goal of optimization is to maximize profitability, reduce cost, or increase operating efficiency of the plant. Determination of optimization is proceed to distillation column C03. C03 is the last separation unit, which is important and responsible to produce propanol as the bottom product. In our case, the objective function is to minimize the reflux ratio of distillation column C03. For the decision variable, we decide the flow rate of distillate, flow rate of bottom, cooling utility, heating utility, and total utility as the decision variables. For the constraints, the pressure of the C03 is set in between 0.1 and 2.0 atm. Here is the set of data of distillation column optimization. Table shows the set of data consists of pressure of the column, reflux ratio, total utility, capital cost, annualized capital cost, operating costs, and total cost. The lifetime of the equipment is assumed in 20 years. From the set of data of distillation column C03, here is the relationship between the pressure of the column and annualized cost total utility in form of graph. According to figure, it can be determined that the lowest reflux ratio obtained is 1.93 at 1.5 atm. Here is the list of formula for the utility saving percentage and the cost saving percentage that can be calculated for the next slide. Next, here is the comparison before and after optimization for the distillation column C03. For column C03, the optimum pressure obtained is 1.5 atm, as the optimum total utility and annualized total cost is obtained. The total utility saved is around 1,800 kilowatt. The percentage total utility is around 7.32%. Total cost saved is around 60,781 ringgit Malaysia. Percentage total cost saved only 1.29%. It is shown that it is less than 5%. It is because of low operating costs and also the factor of the lifetime of equipment, which is 20 years. Furthermore, if the lifetime is reduced to less than 20 years, then the total annualized cost will be more safe compared to the recent value. Next, we moving on to optimization for the cryogenic column C02. The objective function for the C02 is to minimize the reflux ratio of cryogenic column, same as the distillation column. The decision variables is still the same, which is flow rate of distillate, flow rate of bottom, cooling utility, heating utility, and total utility. For the constraints, the range of pressure C02 is set in between 25 and 31 atm. Here is a set of data consists of pressure of the cryogenic column, reflux ratio, total utility, capital cost, annualized capital, operating cost, and total cost. Still, the lifetime of the equipment is assumed in 20 years. From the set of data of the cryogenic column, here we can see the relationship between the pressure of the column and annualized cost total utility in the form of graph. According to figure, it can be determined that the lowest reflux ratio obtained is 1.55 at 29 atmospheric pressure. Here is the same formula that we can use to identify the percentage of the utility saving and the percentage of the cost saving. After we obtain the optimum pressure, which is 29 atm from the graph, we compare the optimization before and after for the column C02. As we can see, for the optimum pressure in 29 atm, the total utility saved is 269,000 kilowatt, and for the percentage total utility saved is around 37.89%. For the total cost saved, it is around 270,765 ringgit Malaysia, and the percentage total cost is 5.493%. The percentage total cost saved is more than 5%. Indeed, it is true that the usage of cryogenic column really helps in reduce the energy consumption, thus reduce the utility of the condenser and reboiler of the equipment efficiently.
Assalamualaikum and good day. My name is Muhammad Najib. So for my part, I'll be talking about the equipment sizing and mechanical design. So for the first part, we will be talking about the equipment sizing, and then later on we'll be discussing on the mechanical design. So first off, I would like to touch on the standards that we use. So throughout the process of designing, sizing in particular, we use plenty of standards in order to determine the right dimension of our equipment. So I won't actually be talking about all of the standards that we use, because that will be quite impossible to cover it all in this slide in a limited amount of time. But I will cover a few of them, and more of them will be covered in the specification later on. So as you can see in the screen here, this is the ASTM standards that we use for our pressure vessel. And these are some of the standards that we use in the sizing of HEN, heat exchanger, pump, and also expander. So next, let's take a look at the equipment sizing. So now we're moving on to the equipment sizing. So there's a lot of equipment to be covered, so I will only go briefly for each equipment. So for each equipment, we'll be discussing on the specification and some sample calculation for the sizing. So as you can see on the screen here, this is the specification for the compressor. You can see that the type of compressor that we use here is centrifugal. And then you can see the electric motor drive, steam turbine drive, the material used, stainless steel. So, and there's other specification involved, such as the specific heat ratio, volumetric flow rate, density, motor efficiency, motor factor, and material factor. So right here you can see we have listed the different type of compressor that we use, and also the specification for each of it. As you can see, the specification involve the method of construction, inlet and outlet pressure, inlet and outlet temperature, volumetric flow rate, and the horsepower. Here is the specification for the expander. As you can see, we listed the same type of characteristic, such as the type, motor drive material, and so on. This is the specification for each different expander that we use. Also include the same characteristics. This is the sample calculation for the pump. First, release the data such as the volumetric flow rate, the density, pressure of the inlet and outlet, and then we calculate things such as the pressure difference, pump head, and also the S. Here is the sample calculation for the mixer. So first, we obtain data from Aspen-ICs, such as the volumetric flow rate and the rotation time. From there, we can calculate the volume of the vessel, so you can see in section B, and then we assume the LD ratio in section C, and then in section D, we can calculate the internal diameter and also the height of the vessel. This is the sizing for the distillation column. First, we list the data such as the mass flow rate of the liquid and gas, the density and such, and then we calculate the surface tension, surface tension factor, FST, foaming factor, FF, FHA, whole area factor, and such. All the calculations were done in the Excel, so for the sake of simplicity, I will only list out the results here. This is the calculation for the sizing of flash column. it goes through the same process for the calculation for the decision column as before. We list out the same data, and then we calculate all the parameters that were needed to get the diameter. This is the calculation for the sizing of cooler. First, we calculate the log mean temperature. After getting the log mean temperature, we can plug in into the equation in section B to get the surface area contact. Through that, we can get the pressure factor in section C. Right here, we have the calculation for the sizing of heat exchanger. First, we calculate the log mean temperature, and then we find the correction factor. Then we plug both of them into the equation in the bottom right to get the surface area contact. So now we're going to take a detailed look of the mechanical design. In the mechanical design part, I'll be discussing on equipment such as the pump, distillation column, and reactor. So the mechanical design is focused on elements such as the stress analysis, structural construction determination, and protection of the vessels. So, the detailed mechanical design is actually based on the book that we use, the Product and Process Design Principles, for the edition, and also the code and standards such as the SME and TEMA and such. So the list that you can view here, this is the pump specification data sheet. You can see here we listed things like the identification, item number, the function, the operating condition, and also the specification such as the material of construction, case speed rotation, type of motor enclosure, and such. So right here we have the drawing of the equipment. As you can see, we have carefully detailed out every dimension. Each dimension that is crucial in building this particular equipment. Alright, this is the equipment specification sheet for the distillation column. The list goes just like before. We have the identification, operating condition, and also the specification. But we added the equipment properties for the tray. You can see the number of tray here is 30, and material used for the construction is stainless steel, and the material factor is 1. So this is the drawing of the distillation column. As you can see, we have listed every part of the component very detailed, each with their respective dimensions. So as you may not see here, I will zoom the image on the next slide, and we'll see it there. So this is the zoom image of the drawing of the distillation column. As you can see, it's very detailed. We listed every part of the component, each with their respective dimension. For example, you have this rectifying plate here, 15 rectifying plates with 9100 mm. As a note, the dimension is in mm, and the total height is 27,000 mm. And each of the list goes on. Right here we have the specification sheet for the fixed bed reactor that we use. As you can see, we have listed the identification, the item number, the function just like usual, the operating condition and specification, and we add the head enclosure design down below. In there we have the type. We use the Elpsarder type, and the material used for the construction is stainless steel. So here we have the drawing of the fixed bed reactor. So you can see it's very detailed. We have listed every dimension that is needed, the length, the height, the number of holes, as you can see down here. And this is the cross-sectional view of the reactor. As you can see, we have the dimension of the hole, the size of the hole, the diameter, and everything.
Now I'll be explaining the equipment costing for all equipment in our plant. Before that, we start with chemical engineering cost index, which is to account for fluidity of money value over the years. All purchases costs are required to be adjusted according to current chemical engineering CE cost index value, as shown as, for example, we use a base cost index in year of 2030, 567, and for the current cost index in year of 2019, which is 607.5. This is the purchasing cost of process equipment. We need to calculate the purchasing cost of the equipment because from the purchasing cost, we can calculate the value of total bare module of the equipment. From that we can calculate the GRC cost. As I mentioned earlier, this is the total bare module cost, which is around 347 million ringgit, which include all the equipment in the plant. Next, we calculate the grassroots capital, which is around 697 million ringgit. We also calculate the total capital investment cost, which is around 2,068 million ringgit, which include fixed capital investment costs, working capital and startup costs.
Next, we continue with the next chapter, which is waste treatment. In this propanol production plant, the stream that connected directly to the waste treatment plant are stream 30, stream 34, and stream 36. Table below shows the composition of compound for each stream that related. There are a lot of treatment alternatives for various types of hazardous components in waste streams of different physical forms. However, capital and operating costs need to be taken considered in choosing efficient and improvable waste treatment. For this propanol, there are two alternative methods that are suggested to treat any waste contaminant from the plant, which is option 1, build waste treatment plant, and option 2, send waste to Kualiti Alam. For the first option, which is build waste treatment plant, below is the process flow diagram that summarizes all the process in waste treatment plant that started from the equalization tank until the filter press. Here is the cost estimation for the first option. The total cost that calculated is around 10,191,000 ringgit. Next, for the option 2, which is send the waste to Kualiti Alam. So the waste from the stream 30, stream 34, and stream 36 will be collected from the production and then will undergo some cooling process until the temperature will reach 35 degrees C, and then the waste will be stored in the storage tank in the large amount. Here is the cost estimation for the second option. The calculated total cost is around 79,203,000 ringgit. After undergo some comparison between option 1 and option 2, option 1 is chosen to treat the waste treatment for the propanol plant since it is more economically feasible compared to option 2. The total cost for option 1 is around 10 million, which is much more cheaper compared to option 2. Option 2 cost is higher due to large amount of waste in this plant will be collected first and then delivered to Kualiti Alam. Therefore, it requires a lot of demand of transportation and treatment service compared to building on wastewater treatment.
Next, we move to the process control. Process control indicates the condition of plant process where any upset can be controlled and following emergency action to be implemented. Without suitable and reliable process control, unupdated process accuracy cannot be monitored. The purpose of process control is to keep process operating parameter without narrow bound of the reference value of set point. There are a few benefits of the process control. The first one is process control can ensure consistency. The next one can reduce the labor cost and can improve quality with higher level of safety. We move to the distillation column. The first one is to control pressure of column at a desired pressure. Next, to maintain column level at desired set point. Second, to control composition of product purity. To maintain level reflux drum at desired set point. And the last one, to maintain bottom temperature of column at desired temperature. We move to the reactor. The first one to control temperature inside reactor and to maintain reactor level at desired set point. For the heat exchanger, we control the temperature of outlet process stream of shell side. For the compressor, we control the pressure of outlet stream. For the mixer, we control the ratio flow rate of the fresh feed stream with the recycled stream at desired ratio, and the second one to maintain mixer level at desired point. For the pump, we control outlet stream pressure, and the last one for the cooler, we control temperature of outlet stream.
Now we move to Chapter 9, Process Safety and Risk Management. Plant safety, external factor and strategies. Every chemical storage is not be situated adjacent to the urban development. Extra precaution on flammable gases and liquids which are capable of causing a vapor cloud explosion VCE. All piping systems located outdoors should be insulated and heat traced to avoid unwanted hotspots, which can result in vapor formation and accumulation by end propeller. Under housekeeping, all of the substance must be stored appropriately and must not be placed under the safety showers or locations which may block the access to firefighting equipments. The spillages of particle hazard liquids and accumulation of dangerous must be clearly stated in the standard operating procedure to be followed properly. The function of utilities is routing of service supply should be secured from the disturbance or hazards to ensure the consistent supply. And under transportation, hazardous properties of product or chemical should be clearly stated so that people all stages of the transport chain are aware of them. Plant location on-site and off-site consideration. Risk assessment for chemical plants should already be performed. This plant location must be constructed in a spacious manner to facilitate regular inspection, which in turn is needed to ensure good housekeeping. Positioning of occupied buildings. The distance between occupied building and plant building will be governed by the need to reduce the danger of explosion, fire, and toxicity. Plant safety. In plant safety, there will be an active protection system to safeguard the equipment from hazards overpressuring in severe cases explosion. There are some valves such as pressure relief valve, restriction orifice, control and non-return valves, emergency valves and interlock system which help prevent a machine from harming its operator or damaging itself by preventing one element from changing state due to the state of another element and vice versa. Worker safety. Every worker must follow safety rules such as no smoking or eating when entering the plant, no drinking of alcoholic liquor before or when entering the plant, and safety instruction and danger signs must be clearly shown, observed, and followed. And all workers must be wear personal protective equipment (PPE) such as safety shoes, helmets, safety glass, and face shields. And every worker must be ensure there's a first aid in their place. The first aid should be placed at the easily reachable location. First aid must contain adhesive strips, wound dressings, gauze pad, and gauze bandage. And the safety monitoring must be done to educate the workers themselves on the safety aspect of the plant. And all workers have the obligation to enforce safety rules and safe working practices according to the designated standard operating procedures, which is SOPs, within the plant. Hazard and operability studies. Here we see the major equipment used in our plant, which is reactor, heat exchangers and mixer. First we move to reactor. The parameter is flow reaction. In flow, if there is no flow, it will be cause failure of control valve, pressure is too low, pipeline leakage, and the consequences is production may be lost and no reactions occur. The action must be required is install flow sensor indicator, clear all pipe blockages, install backup valve for the feed pipeline, install temperature and pressure controller, and regular maintenance. And for reaction, there will be, if there is no reaction, it will be lead to leakage and catalyst failure and production loss and downtime to overall processor. The action required will be add flow indicator controller, install temperature and pressure, add flow arm, and replace a fresh catalyst. There is some consequences if the guide words, if the parameters are used in reverse, or the reaction may be less or more. Apart from parameter flow and reaction, here temperature, pressure, and composition are recorded for reactor. Now we move to HAZOP study on mixer. There will be only one parameter, which is flow. If there is more flow, it will be cause control valve failure, preceding instrumentation failure, which will be possible consequences to cause surges of material flow in downstream and may overload and flood the mixer. Overflowing might occur. So the action required is install flow indicator, controller, and high flow alarm at mixing vessel. Hezop study on heat exchanger. The parameter is feed flow. If there is no feed flow, it will broke the heat exchanger tubes or pipes, which will be consequences to not achieve desired temperature. Energy recovery cannot be achieved. So the action required will be install flow indicator and install temperature indicator. And there is possible less feed flow, more feed flow, and be reverse feed flow. And the action required is discussed carefully. Apart from feed flow, there will be temperature and pressure are the parameters. So the temperature if less, there will be some consequences and causes. So there will be action required such as install low temperature alarm and indicator. For pressure, if there is more pressure, it will because the high pressure at both ends of process stream, which will be causes the tube may crack and shell tubes may burst. So the action required is install high pressure alarm at both inlets and streams.
Next, I will be presenting about profitability analysis. For grassroots capital (GRC), it is estimated around 698 million ringgit, which include total module costs and auxiliary costs. We also calculate total capital investment cost, which is 2,068 million ringgit, which includes fixed capital costs, working capital, and startup costs. Next, we also calculate the manufacturing cost. It is estimated around 6,690 million ringgit of total manufacturing expenses, which include the direct production costs, utilities, miscellaneous, and also indirect production costs. We also calculated the value for depreciation, which is 70 million ringgit, revenue from sale, which is 7,631 million ringgit, net annual profit after income tax, which is 421 million ringgit, and then we calculate after tax rates of return, which is 21.22%. These all the assumptions that we made in order to do cash flow analysis. Firstly, total operating period of N Propano plant is 20 years, excluding the 3 years for the plant construction, with a fixed capital cost investment of 1,723 million ringgit. Secondly, sales income for the first operating is assumed to be only 92% of the designated income, and the third one, for the first year, 25% of TCI is loaned from bank. For the second year, 30% of TCI is loaned from bank, and another for the third year, 35% of TCI is loaned from bank, including working capital. Moving on to the next slide, this is the table of undiscounted cash flow. The data from this graph will be used in order to plot the graph of cumulative cash flow against the year. This is graph for cumulative annual cash flow against the year. From this graph, we can obtain the payback period. For cash flow profile interest equal to 0%, the payback period is 5 years. Meanwhile, this table is for discounted cash flow. The data from this graph will be used in order to plot the graph of cumulative cash flow against the year. This is the graph for discounted cash flow profile. As we can see, we are calculating for interest equal to 5%, 10%, and also 16.9%. As for the conclusion, the total capital investment (TCI) is 2,068 million ringgit. The total expenses for the plant is 6,982 million ringgit per year. The total revenue from sales for the plant is 7,631 million ringgit per year. For after-tax rates of return is 21.22%. The plant life is 20 years, excluding 3 years of the startup period, and the last one The maximum discounted cash flow rate of return DCFRR is 16.90%. With all that, thank you.